As we peer into space, we begin to wonder about the origins of the many astronomical objects, the galaxies and stars, the planets and the moons. In this lecture, the 34th of the series, I'm going to examine the hypothesis that all stars and planets form from the gravitational attraction of dust and gas in space. That's called the Nebular hypothesis. My outline is simple. First, we're going to take a quick look at the many objects in our own solar system. Our solar system is littered with planets and moons, comets, asteroids, and much more. We'll see how space scientists gather information about the composition of those objects, about their distribution, about their dynamics. Those data provide strong hints about the origin of our own planetary system. After that introduction, I'm going to review the nebular hypothesis. This was first proposed by the French mathematician Pierre-Simon Laplace more than 200 years ago. We'll look at the likelihood that our solar system is much like solar systems forming around other stars. And I'm going to conclude the lecture with a quite unlikely story of the formation of Earth's moon. Before discussing the solar system and its origins, it's appropriate to review what we've learned about the origin of the universe itself. Recall that three different kinds of observations provide compelling evidence for the Big Bang theory of the origin of the universe, the idea that the universe originated at a point in time and space and has been expanding ever since. The first line of evidence was the universal expansion itself, described by Edwin Hubble. That's the idea that more distant galaxies are moving away from us more rapidly. Data from the redshift provides compelling evidence then that the universe is expanding. We also have evidence from the cosmic microwave background radiation. This discovered by Arno Penzias and Robert Wilson of AT&T. They saw that the universe is pervaded by a constant flux of electromagnetic radiation, microwave radiation that comes from the actual origin of the universe. The universe has been expanding. That microwave radiation has been stretched out. Till now, the universe is at about 3 Kelvin average temperature. And finally, a third line of evidence, the distribution of light elements, particularly the ratio of hydrogen to deuterium in the universe, provides an additional line of evidence how the Big Bang took place. Now, further analysis, as we saw, revealed that the age of the universe is about 14 billion years. Also, estimates of the total visible mass in the universe suggest that the universe may continue expanding forever. There's just not enough mass to prevent that expansion from just going on and going on. So we may end up with a universe that just peters out, gets cooler and cooler, the heat death of the universe. From these insights, it's clear that the Big Bang filled the expanding universe with matter and with energy. Almost immediately, gravity began to pull this matter and energy into clumps that would eventually become stars and galaxies and clusters of galaxies. Peering through our most powerful telescopes, we observe extremely distant and therefore extremely ancient objects. Using Hubble's Space Telescope, we've glimpsed back in time to the first billion years of the universe. We can observe galaxies that are more than 10 billion light years distant. By that time, by the time that the universe was just a few billion years old, it was littered with countless galaxies, each with hundreds of billions of stars. Now, these observations are critical to understanding the process by which stars form today. Think about it. The universe is more than 10 billion years old, but we see numerous, massive, very large stars, stars that burn out in a billion years or less. This means absolutely that there must be stars forming today. The star-forming processes have not stopped. Furthermore, all stars gain their material from previous stars. So therefore, stars have to be feeding somehow off the cosmic dust and gas that's released, for example, when stars explode. Now, our galaxy features vast regions that are rich in dust and gas. We see exploding supernovas. They add more raw materials for new stars. And the process seems to be this. You get a cloud of dust or gas. The supernova explodes and sends out a new shock wave of mass. And as that mass interacts, as dense shock waves occur, this seeds the beginnings of new stars. You form concentrations of mass that then start sucking in more mass, and that appears to be the beginning of many stars. In this lecture, we're going to see how stars and planets form from just such a cloud of dust and gas. But first, I want to review some of the characteristics of the objects that form our own solar system, because these objects provide important clues to origins. The solar system. The solar system includes all of the objects that are gravitationally bound to the sun. And the sun, remember, is just an ordinary star. In trying to deduce its history, we first have to collect observations about the physical and chemical characteristics of the solar system. Now, with telescopes, we can observe that there are 9 planets, including the Earth, that orbit the sun. There are 4 inner planets. These are called the terrestrial planets. They are small, rocky worlds. They include Mercury, the planet closest to the sun, then Venus, which is enshrouded in a cloudy atmosphere, Earth, the planet of life, and Mars, the red planet. These 4 terrestrial planets are small worlds compared to the next 4 planets, which are gas giant planets, composed primarily of hydrogen and helium. They include Jupiter, the largest of all the planets, Saturn, a planet of magnificent rings, and then Uranus and Neptune, 2 planets that can only be observed with telescopes. These 4 planets are also called the Jovian planets. Then, farther out still is Pluto, and as we'll see, Pluto is an odd object. It's much smaller than the Jovian planets. It also appears to be somewhat rocky. Indeed, according to a vote that's coming up pretty soon by astronomers, Pluto may not even be considered a planet much longer. And we'll talk more about that in 2 lectures. In addition to the planets, there are many other objects that are bound to the sun. For example, most of the planets have 1 or more moons. The Earth has a single moon, a very large moon. Mars has 2 very tiny moons. And then Jupiter and Saturn have more than a dozen moons each. The gas giant planets all have rings, magnificent rings made of tiny particles that have been swept out into a very thin band around those planets. We see asteroids. These are rocky objects, usually quite irregular in shape and ranging in size from small boulders to those objects that are hundreds of kilometers across. There are many asteroids, and most of them, more than 10,000 documented ones and perhaps 50,000 or more that are a kilometer or more in size, are found in a belt between Mars and Jupiter. That's called the asteroid belt. There's also a growing number of known asteroids that actually have highly elliptical orbits, orbits that cross the orbit of the Earth. These Earth-crossing orbits of asteroids are therefore quite of interest because some of these asteroids might actually hit the Earth someday. Then we have comets. Comets are like dirty snowballs in space. They're rich in volatiles, water and methane and other volatile materials that boil if they're brought close enough to the sun. Far out from the sun, they're just condensed snowballs. As they come closer and closer to the sun, those volatiles evaporate, forming a stream of gaseous particles, a stream that's pushed away from the sun by the solar wind, and so you see the great comet tail sweeping around the sun as the comet wends its way back to the depths of space. Comets have extremely elongated orbits. Some of them, indeed, have orbits of tens of thousands of years and extend far, far beyond the planets, the farthest planet. Some of these comets may originate in another object of the solar system, a hypothetical belt called the Oort cloud, which is supposedly lying far beyond Pluto and would be the seeding ground for all the comets. Now, beyond Pluto also lies the Kuiper belt. This has a large number of enigmatic objects in orbit. We can just barely see some of these with our telescopes, and they're just now being understood. Well, most of our observations and most of our knowledge of the solar system comes from telescopes and space probes that actually photograph and sample these objects. But occasionally, we actually have a physical sample of objects outside our own Earth to study. And I want to look at some of these in some detail. This is important data for understanding the origin of the solar system. Of greatest importance are the meteorites. Meteorites are rocks that fall to Earth from space. Meteorites fall on every part of the Earth, every part of the surface. They fall primarily on the oceans, of course, because 3/4 of the of the Earth's surface are oceans. But many meteorites fall on land as well, and occasionally these are recovered. Now, In most places, when a meteorite's found, it's an iron meteorite. It's a chunk of iron that's got corroded and pockmarked surface from the flight through the atmosphere. These are very distinctive rocks, and they stand out from the other rocks on the surface of the Earth. But many times, meteorites are also stony, and those are much harder to spot on the ground. For this reason, scientists are especially interested in a new set of meteors that have been found in Antarctica. The meteorites on the plains, the ice plains of Antarctica, are a unique and valuable find. In this situation, you have plains of blue ice, old ice that have been there for thousands of years. And when a meteorite falls on that ice surface, it just stays on the surface. It doesn't get buried. It doesn't get eroded or weathered. And so scientists take their vehicles and their helicopters up to these flat surfaces of ice, and they glide across the ice. They look for these black objects on the surface, and they have found thousands of meteorites concentrated on that ice surface. Now, these meteorites are very important because they give us a random sampling of objects from space. You find some irons, you find some stones, you find some stony iron meteorites where you have a mixture of metal and other minerals together. And that random sampling gives us the best clues about the distribution of mass and matter in the solar system. Now, while the vast majority of meteorites appear to be fragments of asteroids that have collided and broken up and sent their fragments flying off, a small number of these meteorites appear to come from the surface of Mars. This is astonishing. The way we know this is because Mars has a very distinctive atmosphere, the CO2 atmosphere. And if you look at these supposed Martian meteorites, they're tiny air bubbles that have been trapped, and the air is exactly matching the composition of Mars. Well, how does this happen? How can you get a meteorite from the surface of Mars? The idea is that you have a large asteroid or comet coming in, smashing into the Martian surface. That impact is so energetic that some of the Martian material is ejected into space in a violent event. It must be amazing to see something like this. And then those become objects that are floating around the sun. Some of those things blasted off the Martian surface eventually may come to Earth as a meteorite, a rock from space. We're also very excited about the prospect of actually collecting Mars rocks, and NASA's planning a sample return mission from the Mars surface in the year 2005. And I'm really excited about that. Our laboratory is thinking about ways that we can analyze those rocks and learn more about the history of Mars and the other planets from those samples. One of the greatest set of samples we have are the samples returned from the Moon. Primarily the hundreds of kilograms of samples of rocks and soils collected by the Apollo astronauts. There were 6 Apollo missions that landed on the Moon, and each of those missions brought back samples. And I have to tell you a story about my old thesis advisor, David R. Wunz. David Wunz was a geologist at MIT when I was a graduate student there. And he was on the very first Apollo sample return team. This is what they had to do. The first Apollo sample carried back about 21.5 kilograms. That's roughly 47 pounds of moon rocks and dust. And they were sealed. For 50 days, they were quarantined with 30 scientists to study those samples. Because the scientists couldn't touch the samples at first, they had to do everything remotely in glove bags. It was a tedious prospect, and being cooped up with some 50 pounds of moon rocks for 50 days must have been no treat. But of course, this was the first sample of the moon that had ever been brought back. This is incredibly exciting. Well, eventually he was allowed to come back to MIT and bring a sample of moon rock with him. But so valuable were those rocks that he had an armed guard standing by him with gun at side. This huge hulking man next to Dave Wunz, who sort of was walking down the corridor and looking up at the guard. Dave Wunz had to transfer a small amount of moon dust from one vial into a second vial so it could be split into 2 pieces for 2 different researchers at MIT. And he was so nervous. His hands were shaking so much that the moon dust spilled, and he got moon dust all over his fingers and thumb. Well, eventually the sample was separated. The guard took the other sample away and walked away. And what the guard didn't realize is that we had preserved the glassine, the sheet of paper where you put the sample, with Dave Wunz's thumbprint on it, and it was preserved. It was absolutely illegal at that time to take any samples of lunar materials and keep them, but we sort of mounted that glassine envelope with the faint dust anyway. Shh, don't tell anybody. But that was really a great time. It was an amazing time to be a space scientist. Okay, there are other samples as well. There are things called the interplanetary dust particles, or IDPs. These can be collected in high-altitude aircraft. They're dust particles that come from collisions and other sorts of things in space, and they form literally a fine dust. NASA collects them using an old U-2 spy plane that can fly at high altitude and has collectors and just sort of sweeps up these dust particles. Now, most of them are debris from our solar system, but occasionally, maybe 1 in 1,000 particle is actually a piece that came from before the solar system. It's a piece of supernova that's exploded. It's a piece of a red giant wind, the great solar flares, the winds that came off red giant stars. It's just amazing particles that tell us about the earliest history of our universe, not just our solar system. So that's an exciting area of research as well. Anyway, that's a quick review of the kinds of samples that we have, our precious hoard of physical samples. A hoard that's sure to grow as we have more and more exploration of our solar system. Let's look at the distinctive properties, the characteristics of the objects in our solar system. Because our solar system has many objects and their systematic behavior that tells us something about its origin. First, I want you to consider the very non-uniform distribution of mass. The Sun is roughly 1,000 times more massive than everything else in the solar system put together. 99.9% of all the mass in the solar system is concentrated right at its center. Of the remaining mass, Jupiter is more than twice as massive as everything else. So here you have one huge mass in the center, one pretty large mass in Jupiter outside, and everything else is basically trivial in the context of the total mass of the solar system. Now also, think about the orbits of planets in the solar system. And this is another intriguing similarity. Even though the Sun is by far the most massive object, first of all the angular momentum, that is the rotational energy of the solar system, is held in the planets. Indeed, Jupiter and Saturn, the largest planets, contain by far 99% of all the angular momentum of the solar system. So that's another curious fact. The mass is concentrated in the middle, the angular momentum is concentrated out in the Jovian planets, the giant planets. It's curious to look at the orbits. All the orbits are almost exactly in the same plane. You also find that almost all the planets rotate on their axes in the same sense of the planets orbiting the Sun. So, for example, if you look down in the northern hemisphere of Earth, all the orbits appear to be counterclockwise. Now, this uniformity is surprising in the sense that if you think about Newton's laws, any orbit is possible. You can go this way, you can go that way, you can go this way, or whatever. If you've got the Sun as a mass, the orbits of the planets could be any which way. But they're all very much lined up in a plane. By the way, that's the plane of the zodiac. The 12 constellations of the zodiac sort of line up on the same plane as the planets. And that's why we call it the zodiacal plane. Now, we also learn about the solar system's history from the age of its matter. We can use radiometric dating using things like uranium, lead dating to determine the age of various objects. The moon, for example, moon rocks display a variety of ages, up to about 4.5 billion years, as young as 3.2 billion years for some of the rocks that were brought back from the moon. Many meteorites also display an age of about 4.5 billion years. So these ages suggest that the solid material in the solar system may have first crystallized roughly 4.5 or a little bit more, maybe 4.6 billion years ago. And from this, then, we date the age of the solar system. The solar system is now said to be 4.5 or 4.6 billion years old. And now let me tell you about the generally accepted model for the formation of the solar system. This is called the nebular hypothesis. And it takes all of these different kinds of information and merges them into one hypothesis that seems to match all the observations. The theory was proposed by Pierre-Simon Laplace. He lived from 1749 to 1827. Laplace was a French mathematician with a strong interest in physics and in astronomy. He was a brilliant mathematical prodigy. He became a university professor at the age of 19. And he described his theory, the theory of the nebular hypothesis, in an extremely popular work translated to be the exposition of the system of the world. It was published in 1796, just over 200 years ago. Now, Laplace was a scientist's scientist. He seemed to speak for all scientists. For example, on his deathbed, this is what he said: It's a sentiment that's rarely expressed by scientists, but most of them think it. He said, quote, "The knowledge we have of things is small indeed, while that of which we are ignorant is immense." Well, Laplace added greatly to our knowledge by pointing out the nebular hypothesis. And according to this hypothesis, gravity attracts dust and gas into an ever denser and more compact cloud. Now, the composition of this nebula is going to be primarily hydrogen and helium, because that, of course, is the primary elements of the universe. In fact, depending on how many prior supernovae there have been, it will depend on how many heavier elements you get. The very first stars had only hydrogen and helium and a little bit of lithium to work with. But after the first supernova, you had more and more heavy elements. And an estimate of our solar system is it's about 90% hydrogen, the rest other elements, and that may represent 5 or 6 or 7 cycles of supernova feeding into the material that now has gone into our solar system. Okay, we have now a collapsing cloud of dust and gas. And as it collapses, the temperature at the center gets hotter and hotter because of the gravitational potential energy that's released as the dust comes closer and closer in. Also, the cloud begins to rotate. It has little swirls and eddies that were random at first, but as it gets more and more compact and condensed, the predominant eddy becomes in one direction, and the whole system begins to rotate and spiral. And eventually the solar system begins to look like a flattened disk of matter with a central bulge, not unlike the way a galaxy looks, a spiral galaxy looks in cross-section with that central bulge and the spiral arms coming out. Most of the mass gets pulled to the center. That's where the proto-sun, the pre-sun, gets hotter and hotter, and pressures get higher and higher inside this hydrogen sphere. At some critical point, nuclear fusion reactions begin. The pressure and temperature get so hot that hydrogen begins to fuse to helium, and then the star is born. And when that happens, energy starts radiating out from the middle of the proto-sun to the surface. And then you begin the radiant energy coming from the sun to the other parts of the nebula. The solar wind starts blowing outward at a very high intense rate. And this starts changing and modifying the rest of the dust cloud. The inner parts of the dust cloud are stripped of hydrogen and helium, which are much too light. They're pushed to the outside. What's left are more rocky, condensed materials, and this becomes the 4 rocky or terrestrial planets. Planets that have very little hydrogen and helium relative to the other objects in the solar system. Farther out, where it's cooler, where the solar wind isn't so intense, the hydrogen and helium can condense to form the great Jovian planets, the gas giant planets, first Jupiter, and then Saturn, Uranus, and Neptune. Well, this is a wonderful model. It seems to fit the facts. And many astronomers start wondering how likely it is that this same scenario that formed our solar system might apply elsewhere. Well, one way of tackling this question is to devise computer models. Again, computer modeling is so important in science today. It keeps track of the evolution of the dust cloud under gravity, under the condensing cloud, under the first nuclear fission reactions that form the star. What happens to a dust cloud in those situations? Well, one surprise in these computer models is under most conditions it appears that 2 stars should form, not 1. That you should form a binary star. And observations confirm this. Most of the stars we see in the heavens, in fact, 2/3 or more of the stars we see are binary stars with 2 large masses orbiting around each other. In that sense, our solar system is a little bit unusual. Not rare by any means, but certainly less common than the binaries. If Jupiter had been 50 to 100 times larger than it is, we too would be living in a binary system. And Jupiter too would be a star, a brown dwarf star to be sure, but a star. When only one star dominates in a system, calculations show that the pattern of planets we have is very likely. Astronomer George Weatherow, who's at the Carnegie Institution of Washington in Washington, D.C., has made calculations like this. And what he does is he starts by putting 10,000 or more small objects, planetesimals, things that are a kilometer or 10 kilometers or so in diameter, in orbit around the sun, in just random orbits. And then he watches how gravitation pulls these together. And he finds that almost invariably you get 6 or 8 or 10 planets, more or less regularly spaced, arising out of this chaos. The process is fast. It can take place in a few thousand years. And one fascinating aspect of these calculations is the importance of very late-stage collisions, which fix some of the details of planetary behavior. Imagine this, for example, an object like the Earth. Once a large mass forms, it starts sweeping up the other planetesimals in its vicinity. But it's very possible to have two competing large masses near the same orbit. And that situation is absolutely unstable. You cannot have two planets occupying the same orbit. Eventually, those two planets have to collide. And when they do in a late-stage event, it's epic, it's catastrophic, it's violent, and it can change some of the details of planetary orbits. So, for example, Venus appears to be rotating not counterclockwise with the same sense as the orbits. Venus has a very, very slow clockwise rotation against the orbits of all the other planets. This is suggested it may have occurred because of a late-stage collision. And as we'll see a little bit later in this lecture, the Moon is also very likely a result of one of these epic late-stage collisions. Well, we can look from observational evidence and see whether planets form around other stars. If solar systems form from contracting disks of gas and dust, we may be able to see such objects in our own galaxy. And indeed, Hubble's Space Telescope has provided spectacular evidence that this may be true. First of all, we see dramatic images of immense dust concentrations, dramatic fingers of matter that are seen in the Eagle Nebula, for example, which are star-forming regions. We also have captured with the Hubble Space Telescope what appear to be stars surrounded by disks of dust. Now, these may actually be ancient solar systems in their very first million years of formation, solar systems that eventually will have a whole series of planets, but now are still in the dust ring state. Well, I want to end this lecture before I summarize by telling you about the amazing story of the Moon's formation. Current models of the evolution of the Moon and the Earth illustrate planetary forming processes very well, because the Moon is a real oddity in a sense. It's one of the solar system's most enigmatic objects. First of all, it's the only large moon that's part of any terrestrial planet. Mercury, Venus, Mars don't have large moons, but we do. Also, the age of the Moon seems to be very similar to the Earth. It was formed at about the same time, and it's not clear how that might have happened. And curiously, the composition of the Moon is very similar to the Earth's mantle. That is, not its core or its crust, not the average composition of the Earth, but just one layer of the Earth, an outer fairly thick layer. Now, this has significance. How can it be that you have a Moon which appears to have what's called a differentiated composition? See, when the Earth formed, it had one large average composition, but then the iron metal was sucked to the core because of gravity. What was left was a mantle of a different composition. The Moon has that different composition. And it suggests a relationship between the origin of the Earth and the origin of the Moon. So here's what we think happened. We had a nebula. The planet Earth formed in its space around the Sun, but a competing mass, a mass perhaps the size of Mars, was also sweeping up debris in a very similar orbit. Towards the end of the formation of the planets, we then had two objects competing for the same space in the Earth orbit. And those two objects had to collide. The Mars-like object impacted the Earth in an epic collision, an unimaginable collision, and in a matter of seconds, a huge chunk of the Earth's mantle was ripped out and thrown into space. And that molten mass of mantle then it coalesced into the sphere that is now the Moon in orbit around the Earth. A late-stage collision, an epic process, forming our own Moon. According to current models, that's what happened 4.5 billion years ago. You know, the surface of both the Earth and the Moon had to be molten at that point. Not only were radiometric clocks set then 4.5 billion years ago, but many of the other characteristics of the Earth, which we'll talk about in subsequent lectures, arose from that point. This is an amazing story, but as we're going to continue to see, the solar system is a truly amazing place. In summary, the solar system contains all of the objects that are gravitationally bound to the Sun. 8 or perhaps 9 planets, lots of moons, countless comets, asteroids, and more. According to the nebular hypothesis, these objects formed from a great cloud of dust and gas more than 4.5 billion years ago. The sun got most of the mass, and it became the central star. The planets got most of the angular momentum, and they travel around the sun in their orbits. We have 4 interterrestrial rocky planets subjected to the sun's intense heat and solar wind, and then the more distant gas giant planets, the 4 gas giant planets, which are balls of hydrogen and helium, not quite large enough to become stars. In the next lecture, we'll take a closer look at these objects of the solar system.